Right, so I believe that we're live on YouTube. Okay, let's just hit the refresh button and I'll go to the live stream as well. And I'm also going to do a share of the link. So that's our live stream. View live control panel. There we go. And share. I'm going to copy this link, and this link will be available for afterwards and for all time, and I will actually post that on social media just so that it's available on social media for anyone that wants to join. So I'll tweet that out. It's not a tweet anymore, it's something else. We'll exit out. And where we were up to is efficient computation. So it's from our little book of deep learning, and we've got through the machine learning section. And we had our list of contents on the side here, and I was kind of like reading through everything sequentially, and we talked about a lot of stuff. We looked about what was in the, let's just go to the, I guess, the contents. We looked through the contents themselves, this table of contents, and everything here is written for a mobile device, so you could read this all on your phone. That's what this little book of deep learning is for. It doesn't contain everything, but it contains a lot of stuff. It's quite nice to go through. And we have got to basically, so we looked at the foundations, which was machine learning, learning from data, basis function regression, under and overfitting, and categories and models, and that was all in the previous stream. So this current stream is about efficient computation. I believe probably if I click there, yes indeed, it jumps over to efficient computation. As a caveat, I have not read through this. This is all live. Literally, I actually haven't even seen the words on the sections I'm about to cover. I want to do it live because it's quite nice doing something live ourselves. So let's just have a look anyway. So efficient computation, and by the way, even before I begin, because I always forget this and I do it like 2 hours later, which is, if you subscribe right now, click the subscribe button and then discover that it's boring afterwards. It's probably better that way. Hit the like button first before it even begins, and yeah, that would be quite helpful. Useful. It would increase my follower count. Every single person that joins increases the follower count by about 2% because I've only got 50, so that'd be very nice. Apart from that, let's continue then. So efficient computation, what does this all refer to? And I kind of alluded to it maybe at the beginning, but well, I guess the words are going to say it anyway, so I'll do a little read through and then maybe go through it if it needs further explanation. From an implementation standpoint, deep learning is about executing heavy computations with large amounts of data. The graphical processing units, known as GPUs, have been instrumental in the success of the field by allowing such computations to be run on affordable hardware. And we discussed Moore's law and effectively the doubling of computational power or number of transistors and the halving of the cost. And that law was observed 20, 30 years ago, and everyone was like, yeah, that it's going to be true for the next 10 years and then it will stop. But there's been all of these different techniques that have happened, and basically our computing power has just basically continued to double, and the cost has just continued to drop. Unlike many other things in society where the cost has increased, compute power has just become more and more efficient. It's become cheaper in relative terms. So we've just got this power, and now all of a sudden we can do all of this stuff that we couldn't do before, and this is the advent of everything in the whole AI space, because it needs this efficient computation and needs this power available to it. So that's the graph. These GPUs, they've come about and they've been instrumental for that, and actually they've helped in things like cryptocurrencies, like Bitcoin, for example, which needs a blockchain, and again it needs a whole bunch of GPUs because the processing power is actually quite large now. It provides an extremely secure way of for cryptocurrencies, but we're looking at a different space. But it just applies across the board for many things. So the importance of their use and the resulting technical constraints on computations can be done efficiently force the research in the field to constantly balance mathematical soundness and implementability on novel methods. Like, we just try to maximize what we've got available to us. People who were doing computing 25 years ago, 30, 40 years ago, they just didn't have the space in terms of like computational space, like the storage space. They weren't even using like cloud storage. That they might have been using CDs, and before CDs they were using floppies. So they didn't have this. Not only did they not have the compute power, but they didn't have the storage space as well. All of these things have increased, and they had to do the best that they could. One thing, for example, is you collect less data, for example, or your sample sizes. You'd just be more. You'd be more efficient with your sampling because you're forced to, and now we can be a bit more generous, but then our data's become bigger. So again, kind of like it's a balancing act. So it goes in and talks about GPUs, TPUs, and batches. So a GPU is the graphical processing units. Graphical processing units were originally designed for real-time image synthesis, which requires highly parallel architectures that happen to be well suited for deep models. One thing I'm just going to do is in the chat, I'll just put a test just to make sure that it's working. Test, there we go, and yeah, it pops up there. So that's all there. So as a usage. So basically, I just do a recap. Originally designed, so it was designed for real-time image synthesis, and this is actually computationally quite intensive. So that's what they were designed for. But we can use these GPUs for other things as well, and they just happen to be well suited for these new deep models. As their usage for AI has increased, GPUs have been equipped with dedicated tensor cores. Okay, this is the TPU, effectively, deep learning specialized chips such as Google's tensor processing units, the TPUs, have been developed. Okay, I guess it's going to tell us what they are, but basically, like, it's just a bit more of a customization, and in particular, GPUs were for graphics and TPUs are for computing tensors. Tensors are kind of like fundamental in AI. A tensor is mathematically, let's see if I can Google one quite quickly. I wonder if I can find a tensor relatively fast. Here, a tensor, not TensorFlow, I'll just do tensor, although TensorFlow is based on all of that. Tensor, there we go. This is probably the a nice imagery description if I can get it there, but a tensor basically is a set, or it looks like effectively a matrix. It can be like this particular one is two-dimensional, but it can be three-dimensional as well. But it's a whole bunch of values that belong into a block in the memory. Effectively, that's a very crude definition of it. A vector is like one line of memory, so like a 1D array. A tensor here, this is a tensor, which is a 2D array, but you can get n-dimensional arrays, so you can go 3D arrays, and it's depicted here in this particular image. Maybe if I click on it, I don't know if it'll. I don't want to go to. Okay, that's just taken us to a YouTube
hey everyone,
video.
welcome to.
So I didn't want to get to tensor calculus videos. But we've got here, we go to we define the top left component, or we define these components by like an x, y, and z, and the top one is x, and x, so it's the first value, the first subscript, and the second subscript is the other component. So so you've got an xx, you've got an xy, and then you've got an xz, and then the next row down you've got a yz, a yy, and then a yz, and finally you've got yz. Now you could use all types of subscripts that go in there, so it could be like t, then row, and then column. So t0 1, so t0 is for the row, and then so it'd be t0 0, t1 1, sorry, t0 1, t0 2, and then it'd be T1 naught, T11, T12, and so forth. So there's all these descriptive ways. It'd be like the Tij, they're the subscripts, and it's kind of like how we talk about tensors, basically. So just jumping back to our little book, maybe we'll get into that, maybe we'll see it in some way. I could create a tensor in, maybe I'll do that at some point in our, I could do that in NumPy quite fast, so we could sort of like produce a tensor and have a look at what a tensor looks like, and maybe do some like basic tensor computations just to see what it looks like as an overview more than anything else. But ultimately, these TPUs are specifically designed to be very efficient for operating on tensors. That's kind of like the global overview summary. A GPU possesses several thousand parallel units and its own fast memory. The limiting factor is usually not the number of computing units, but the read-write operations to the memory. So, CPU. The slowest link is between the CPU memory, that's what's on our actual computer, the central processing unit, the CPU memory, and the GPU memory. Consequently, one should avoid copying data across devices. So we should just go directly to the GPU if we can. And there's ways in things like TensorFlow and so forth where we can point what, whether we want to use a CPU or a GPU, or even possibly a TPU now, I imagine. Moreover, the structure of the GPU itself involves multiple levels of cache memory, which are smaller but faster, and computation should be organized to avoid copies between these different caches. So we can see this kind of like organization of stuff. And Python's kind of like a great example of this, because if I do jump over to this, and I've done this on a whole bunch of videos actually, but it's always worth doing the recap, which is if I jump over to here, or this would be good for drawing anyway. In fact, maybe I will jump over not to Python yet, but I'll create a new page over here. We have you can have a list in memory. So we have this. I should really create an empty block in some way, or let's create like lots of little blocks. So this is kind of like our memory, so like in blocks, and so we can have this list in memory, and it's kind of like spread out all over the place, like somewhere. And so long as we can get from one element to the next element, we've created this like generic list, and Python offers us this generic list. It's a little bit inefficient. You could put in other data types in here. So in one of these, for example, you could have a string, and in another one here, copy, paste, you could have an integer. So you can have all of these different data types, f2, int, right? So you can have an integer in the next one. Let me just draw kind of like a little box around it, I guess, just to show that this is all one kind of like list. So we'll do a fill with, I guess, is there a none in here or something? No, I'll send it to back if I can't do it. Oh, there you go, none at the top, there we go. And kind of like a little dotted line maybe, just because, there we go, that's sort of like our... So that's a kind of like a list in Python. You could have a string, you could have an integer. Here we go, we've got other integers, but nothing stopped us, for example, having a Boolean data type in our list. So it's very flexible, right? But it's inefficient because all of these data types, so this one could have been a bool, right? I have to make one tiny bit bigger, and we could have had, because I got a bigger one, I'll copy that. Whoops, didn't mean to do that. Copy that, paste it, and we could have a float that will take up more. I could have put a string in there as well. Oh, I did the string. So these data types of all different sizes. We don't sort of like know how to allocate the memory, but it's very, very convenient, but it's memory inefficient. So one thing that we do, so this is what I will call, and I should actually write it there somewhere. I'll write it just above it. That's effectively a very cheap, nasty version of a list, right? So that's our list here, our Pythonic list. So the next one that we're going to look at really is this one here, which is copy and paste. We'll go all the way down. We're going to talk about like an array now. Right? An array has a different feature, which is it's homogeneous, right? Which means it must be all of the same data type. So if we have an integer, they all have to be integers. So delete that one as well. Delete. There we go. And I'll depict these ones. So like a Boolean might be more efficient because it can only be a 1 or a 0. An integer is quite efficient, but a string, for example, is not so efficient, so it occupies a bit more memory, and a float occupies a little bit more too over there. So, you know, possibly something like this. Pictorially is how it kind of like looks. And we can also append our lists so we can dump another item into our list. So I should kind of like give that as an option too. So copy paste. In our list, we could sort of like, I want to create another Boolean somewhere, and I kind of like want to stick it into, I wonder if I can do a curved arrow. No, not really. So I just do a straight arrow. I won't be, let's just do an arrow then. But I want to take this Boolean here and to like dump it into here. And put a little circle around it just so we know that's what we've got, and color none, and give it red line, and so there we go. We want to put our Boolean over there, and I might move it around a tiny little bit so it's out there. I know. We've got the idea. Let me make this little line thicker. Everything in here is one piece. So there we go. So we can append our list. We can put things in the middle, at the end, at the beginning, and so forth. So we can treat the lists how we like. They're very, very convenient. But an array is going to be quite different. And an array sort of like looks like this. So if you've got one integer, we know the size of it, and we also know we've got no flexibility now. They're all going to be of the same type. But because they're all of the same type, we know the width of each one of these. So we can now be very efficient with this packing procedure. We can do something like this and kind of like pack them all right next to each other in the memory. And let's get. So it kind of like looks like this. All of a sudden we can see that we need much less in terms of like the memory space and everything here. Basically, these are all integers now, all of them. So it's more a case of int, and then if I expand this, kind of like F2 to go in, dot, dot, dot. Everything here now is an integer from beginning to end. They're all of the same data type. This is called being homogeneous. So we've got this close packing, and we get this like level of efficiency. We're no longer sort of like jumping around in the arrays, and also we do two things, right? And I should write those two things really, at least two things, a couple of more things. But one is that they are the same data type, right? And the other one is that it's a specified size, right? So we don't have this flexibility on size. We shouldn't be like amending the array and putting things in there. We're like just declaring it's this piece of memory somewhere, like it put it all together, and we're going to operate on it, but we want to operate on it really, really fast. So Python's a good language for explaining this because it gives you the feature of this inefficient list, this inefficient but convenient list, but then this efficient array. And the array is, you know, typically it's a NumPy array, and that comes out of C, which is a more efficient language. So it kind of like calls on its parent language C for getting this array. So that's kind of like globally speaking, sort of like what it looks like. So let's just jump back to. So this is achieved by organizing. This is what it's talking about. So like we can get these arrays, or we can make the memory efficient, and we can put them in a certain way. These combinations will just make the computational the processing speed faster, basically. And if we get a whole bunch of these arrays, so it says here we like copying as well. We don't want to move between arrays and things, because the more moves that we do, the inefficiencies come in. So if we got an array, oops, I shouldn't do that one. But if we've got an array like that, then maybe we want to sort of like harness all of its efficiency. So copy this and paste it out there, and kind of like do something like this. We'll copy that. It's like stack them and put them all together in very neat orders. So we want to do something like this effectively. Even if we're going to operate on the batches, we want them all to be contiguous blocks right next to each other. So something like this, and the GPUs have enabled us to do that type of thing. This would be the world's worst example of a GPU, but it's like conceptually we can see this organization coming into place. And if we can, or at least if we can organize it, we get these efficiencies. So I'll probably just rerun over this. So this is achieved in particular by organising the efficient computation in batches of samples that can fit entirely in the GPU memory and are processed in parallel. So when an operator combines a sample and model parameters, both have to be moved to the cache memory near the actual computing units. Proceeding by batches allows for copying the model parameters only once instead of doing it for each sample. In practice, a GPU processes a batch that fits in memory almost as quickly as a single sample. Here we're going to start talking about some numbers. A standard GPU has a theoretical peak performance of 10 to the 13 to 10 to the 14 floating point operations. So let's just write out what 10 to the 13 is. If I can, my signature there. So one, it's kind of like this is 10 to the 12. So it's that many. I'll stick a couple of more zeros in. Or it's something between this one. I don't think I can copy it, but between this one, I mean the writing size smaller, but between 10, I guess, billion is it? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 10 trillion operations or something, floating point operations. So flops is the acronym for it, floating point operations per second. And its memory typically ranges from 8 to 80 gigabytes. So we've got this nearly unheard of, if we cast our minds back, like this nearly unheard of amount of floating point operations that we can do. But now we're talking about big data, so again, it's still limited in the sense that if we're going to operate on a big matrix, we can all of a sudden, when we do our matrix calculations, we can get to that number of operations quite fast. And the reason why is, even if you have a square matrix, let alone a cubed matrix, that we're going up by the power of squared. So if we had like a 1000 by 1000 matrix, the number of operations or number of items in it would be 1000 times 1000. So basically it would be 1 million just there without even attempting to do very much. So, right, we've still a lot of room to get to this number, but as we increase, every time we increase this by 1 0 by a factor of 10, so if we increase both sides by a factor of 10, we've now added on 2 more zeros here. So now we've got to 100 million. So we can see that if we get 10,000 by, so now it's 10,000 by 10,000, we'd have to add on 2 more zeros, 0, 0. And I'm just be careful where I put the commas, but that's 1, 2, 3, 4, 5, 6, 7, 8, 9. That's 10 billion. If we added on a couple more zeros, it'd only be a few more zeros onto this. So if we had like a million by a million, we'd be in the kind of like trillion things already. So that's kind of like the global view of it anyway. So the standard, I'll click on it, I'll leave that number so like down at the bottom. And maybe I can move this one just to, that's kind of like what it is, this number here. There we go. The standard FP32 encoding of float numbers on 32 bits. I think that stands for floating point encoding for 32 bits. The 32 stands for that. Because if it was 64 bits, it'd be FP64. So the standard FP32 encoding on floating point numbers is on 32 bits, but empirical results show that using encoding on 16 bits or even less for some operands does not degrade performance. And that means that we can halve our number of bits, so that we could in theory double our number of data without really degrading performance. And if we observe this as a fact, so we do all of our calculating, we see that we don't get this degradation in performance, then there is some kind of saving to make. And so we can go from 32 bits to 16 bits and possibly even 8 bits and maybe even lower, although possibly not lower, it just depends what we do. We will come back to this in 3.7 to the large size of deep architectures. Okay, so it's talking about that. I'll just hit close just so that all of that said, I can scroll down. So we move on to our second section. So our first section was titled GPUs, TPUs and batches. And our second section over here is called tensors. So now we're going to start talking about tensors. GPUs and deep learning frameworks such as PyTorch or JAX, I don't know what JAX is exactly, so I'll remind myself of it, manipulate the quantities to be processed by organizing them as tensors, which are series of scalars arranged along several discrete axes. They are elements of the Rn1 to Nd. So R means real numbers. This is very, very mathematical notation. So they're just real numbers and they're kind of fitted into this grid. They were effectively this kind of image that I show there. Maybe if I do images, there'll be a lot more images of tensors. But here's a good example maybe of a tensor. It's just a bunch of real numbers. They don't have to be integers, by the way. But you have to have a labeling mechanism. So how do I get this number 8 over here? Well, it's on row number 1, 2, 3. So it's 3 rows. So if in computational space, it's on row number 0, 1, 2. So it's a second index down in terms of rows, and it's on column number 0, 1, 2, 3. So we would index it by 2, 3. That's how it'd look. I wonder, again, I just wanted to see the image and not the whole part of it. But anyway, we can have two-dimensional tensors, so x and y's, which are probably the most common. So that's called a rank. In fact, here in a nice picture down below, it's called a rank 2 tensor. So a rank 1 tensor is really just a scalar. It's just one number. A rank 0 tensor is a scalar, it's just one number. A rank 1 tensor is a vector. So that's what we might call our Python list. And then a rank 2 tensor is what we call a matrix, or a list of lists, and a rank 3 tensor is a list of matrices in a way. So it's 3-dimensional. And in order to, if we can see how the maths extends quite easily, because if we wanted to, if you imagine this cube as opposed to this flat matrix, if I wanted to index a certain point, and here we've got this indexing T01, well, all I have to do is add another index to get the third dimension in there. So I'd have T, the first element would be how many across we have to go, for example. The second element would be how many down would have to go. And the third element would be how many deep would have to go in the Z axis, or the Z direction, or the third dimension, as it was. So I'm just wondering at T11, so that's kind of 1 down, and well, I don't know. Try not to get into the tensor mathematics too much for 2 reasons. One, I need to make sure I remind myself to get it all right. But the other thing is that I think it's going to be possibly a bit too beyond the scope of the little book of deep learning. Well, let's see where we get to. But that's what this notation means anyway. You don't have to be scared of it. It means, I might draw it somewhere if I can. Let's just do a little drawing. So again, we'll go to our thing, and it kind of like means like 9, 100, 20, and then we'll go down 25. Put little spaces in it just to give us a little bit of space. We'll shrink our font as well, kind of like just sort of like these random numbers. 50, 30, 35. I'm trying to be unique on numbers, and then another number here, 15, 0, because we can have zeros are allowed, and 100 over here. So something like this, right? This is what, if I can shrink it a bit more and kind of like put it here, that's really what this means. It's just like our little system of numbers that we understand. So they're elements of this R1 up to ND, that generalized notation of a vector and matrix. And a vector is just one column of that, effectively. So tensors are used to represent both the signals to be processed, the trainable parameters of the models, and the intermediate quantities they compute. So a whole bunch of things. The latter are called activations in reference to neuronal activation. So, and like hopefully there'll be pictures that come later on, but these are kind of like put into layers, and we do like one bunch of computations on another one and so forth, but in an efficient manner using these matrices. For instance, a time series is naturally encoded as a T times D tensor. So this probably refers to T for time and D for like values, I imagine, or for historical reasons as a D times T tensor, with T is its duration, so it's like a time component, and D is the dimension of the feature representation at every step in time. So actually, D is probably possibly an actual vector at each step in time, containing a whole set of values, often referred to as the number of channels. Similarly, a 2D structured signal can be represented as a D times depth times height times width tensor, so like some kind of cube, where H and W are its width and height. An RGB image would correspond to a D equals 3, but the number of channels, so D equals 3 means 3 dimensions effectively, but the number of channels can grow up to several thousand in large models. And what does D equals 3 mean? It basically, our RGB thing here is that they're normally defined as, it's come nice as small text already, but it's 0 to 255 units, and that describes the amount of redness, and then 0 to 255, that defines the number of greenness in the pixelation, and then again 0 to 255. Why 0 to 255? Because 256 is 2 to the power of something like that, 2 to the power of 8, and that means it's 256 wide. So this is 0 to 200. It's kind of like some sort of range, and I put it in the same bit. It's literally describing the red component, then it is describing the green component, and finally it is describing the blue component here. So red, green, blue, and all of the mixtures of the rainbow, again, kind of like, could sort of like, maybe I'll click on an RGB, but the RGB is described like that, and you've got like on your screen, you've got like 1 million across by 1 million pixels down, however many, whatever a high definition screen is. So you've got like 100,000 pixels across and 100,000 pixels down, and each one of them contains this D3, this tuple of the amount of red, green, and blue, and it's sort of like all condensed together, and that's what gives us our image basically. And the more pixels we have, the kind of like the better the image is, and the less pixels we have, the more granular the image is. So that's just generally, that's what a tensor is, and that's what a tensor is for an RGB image, and how it might be used. Adding more dimensions allows for the representation of series objects. For example, 50 RGB image, 50 RGB images of resolution 30 by 24 can be encoded as, so you've got 50, right? So 50, which is, I should go on to really this bit here. That's this 50, as in there's 50 of these little pixels. Then 3 is referring to this number of dimensions over here. So each one of these contains one R, one G, and one B. So it's what each one of these contains. That's where the 3 comes from. And then the 24, 32 by 24 is, I presume it's 50 of resolution. I wonder what the 30 is. That the matrix itself. So it'll be 50 lots of 30 by 24s. So this is like of 32. So this is 32 here, and this is 24 wide, and we're actually going to like plonk 50 of these together. So there's going to be 50 of those. So we can sort of like imagine that kind of like growing out and out and out. And each one of those each one of these little dots in this 30 by 24. Oh, my dots look quite nice going in sequence, but each one of these dots contains 3 pixels. And that's the amount of information that's contained. So that would look like, just even in this calculation, if I shrink it out and get the calculator, it would be 50 times by 3 times by 24 in terms of data amounts times by 32, right? We've already got 115,000 pieces of things that we need to do our tensor. It's quite large already, and that wasn't very much. Like your computer screen, if you're watching it on a monitor or something, will contain, I don't know how many megapixels it contains and how it's arranged. So just something like that. So deep learning libraries provide a large number of operations that encompass standard linear algebra, complex reshaping and extraction, and deep learning specific operations, some of which we're going to see in chapter 4, so we're going to get this in a later chapter. The implementation of tensors separates the shape representation from the storage layout of the coefficient in memory, which allows many reshaping, transposing, and extraction operations to be done without coefficient copying, and hence extremely rapid. So we just get this idea that if we can avoid copying as much as possible, that we're going to gain efficiency. So that's basically the purpose of these GPUs. In practice, virtually any computation can be decomposed into elementary tensor operations, which avoids non-parallel loops and at the language level and poor memory management. And again, it's kind of like referring back to my very crude picture, but like we want to sort of like stack everything compactly, and when we're talking about chips, have them all located next to each other and try not to copy anywhere, and try not even to have to do parallel processing if we can, but we have to. All of the people involved in the development of deep learning, from the designers of drivers, libraries and models to those of computers and chips, know that the data will be manipulated as tensors. This is a huge community of people, like a huge community of very, very sophisticated and quite intelligent people, like very, very focused on a subset of space, kind of like you can imagine the amount of knowledge that has gone into this to making it as efficient as possible. The resulting constraints on locality and block decomposition enable all the actors in this chain to come up with optimal design. So everyone knows what we're working on now. We now understand from this document alone that we're working on like minimizing copying. We know that we're working on tensors, and the more that we can compact our data into this tensor mathematics, the more efficient that it can be. And we used to use tensors a lot back in physics in like imperial, like when you're doing like general relativity, there's a lot of tensor algebra. But that was kind of like three space, and you do things there. But actually, this extends to a much more powerful aspect of it. When it comes to computing, it's much more than that. So I wonder if I should end this little one here, because we're now on chapter 3. I wonder. Oh no, hold on. We're still in the foundations actually. So chapter 3 is training. If I click on it, it's training. So we've talked about machine learning. We've talked about efficient computation, and I guess we're going to talk about training next. Maybe I'll have just a quick look at it, or if I can click this arrow. Okay, yeah, this has got things that are interesting in here, because now I think at least it's going to conceptually talk about it, like losses. It's going to talk about pieces of it. Autoaggressive, okay, we'll be talking about that. Gradient descent, which I mentioned right at the beginning. There's something complicated here, but it's very debunkable. So we'll go through that. Back propagation. So again, we slightly need to understand what this is, but the word backwards, so like looking backwards in our data effectively. The value of depth. We'll see all of this kind of stuff. So I guess only because this is 40 minutes long, it's kind of like more than enough. Sometimes they don't do like 2.5 hours. Where I'll make the next session on training. So although in this little section I actually called it, where was it on my little thing here? Over here, right in the beginning, I called it efficient computation and training a model. I guess over here, and I took training a model from this bit. We'll get onto training in the next section. So yeah, like and thumbs up and all the rest of it. Post your comments, any comments or questions or whatever you might like to see. So we'll see whatever comes out of all of this. Yeah, and definitely follow as well and so forth. So yeah, thanks for the watching, and I'll be continuing chapter 3 on training in the in another